Thank you. It's good to talk to you again. I'm going to tell you about some work that me and my students and several other people have done. This has been a lot of fun over the last year. It kind of got its start because of the solar eclipse. We decided to use GNU radio and USERPs to try to measure different aspects of the ionosphere as the solar eclipse happened, and see how dynamic the ionosphere was during the solar eclipse. And the results were pretty surprising. It was much more dynamic than people actually thought it was. So this began a project supported inside the American Radio Relay League called HAMSI, and it's available to all sorts of people to work with. And I'm going to tell you a little bit about that and some of the things we've done, some of the things we intended to do, solicit your help in these things, and tell you what's been done, show you where to get some GNU radio code, etc. So these set of projects for me has been an excellent place for a GNU radio fanboy who no longer contributes to the GNU radio base code to actually do something useful, I hope. Okay, so let's talk a little bit about HF propagation, just get a quick look at how it all works. This is very schematic. It's not actual, but anyway, it gives you an idea. So the radiation from the sun, mostly the ultraviolet, strips away the electrons on the atoms of the atoms and molecules that are in the ionosphere, the outer reaches of Earth's atmosphere, and it tends to set things up approximately in layers, which vary as the time of day goes. Which one of these is a pointer? That one. Okay, so this is an F layer, it's the highest, and there are a couple of F layers, and the E layer and the D layer. And so the density of ionization in each of these layers is variable. And the variability happens on a daily cycle, an annual cycle, and a funky cycle. Every 11 years, the sun changes, goes through kind of a periodic transition of its internal dynamics, and sunspots happen, and then they go away, and then they happen, and they go away. And when the sunspots are there, lots of energetic particles and other things flow out of the sun and strip the electrons off the atoms, and so these layers become highly ionized. Right now we're in the solar minimum. If you look at any space weather site or grab a filter and look at the sun, you will see that there are absolutely no sunspots at all. And we're well over 100 days in the last year of having no spots at all on the sun. So lots of things can be inferred about the ionosphere from making measurements of various aspects of the ionosphere and relating it to what we see happening on the sun. So this diagram was stolen from an amateur radio operator named Carl, whose call sign is K9LA. Okay, so this is another diagram that I stole from Nathaniel Fursell, who was an amateur radio operator, got his PhD from Virginia Tech in ionospheric science, and is now on the faculty of the New Jersey Institute for Technology. Nathaniel, while he was at Virginia Tech, and Magna Moses, who is still at Virginia Tech, and I and a couple of other people, Carl being one of them, went to the American Radio Relay League and asked them to start this HAMSI activity and to help us promote the participation by amateur radio operators and others into looking at the solar eclipse. So Nathaniel continues this work, and you'll see that as we go on. But this is another diagram of the ionosphere shown in a different way. These are approximate heights. None of this is fixed, it's dynamic, and each of these layers changes density through the day. At night, the F2 and F1 layers go together. They're not separate anymore because this part collapses into that part, and it gets much less dense. So there's not much reflecting going on with this. And these layers down here disappear altogether at night. Okay, so again, what can we do to help with that? Actually, it turns out it's pretty easy, but let's look at a little bit of this first. So here's an antenna, and I want to talk to somebody way over here. So the way we do it is we have an antenna, we transmit a signal, it bounces once or maybe more than once, and winds up here at some signal level. And of course, if you're going to use these frequencies, typically 0 to 30 megahertz in the HF spectrum, you want to have some prediction of how this is going to work so you know whether or not to waste your time trying on a particular frequency. So if you know something about these regions and can predict their behavior, you can decide whether or not that frequency is usable for this station to communicate with that station. Okay, so here, this is oblique or propagation or skip propagation. And many of you have heard of Bragg angles and other things, or you've seen out on the desert or on a hot road a mirage that's way off in the distance that looks like water. Well, when you get to, when you get to that angle where this begins to reflect, it's the same thing as seeing light and sky reflecting off that mirage in the distance. And it changes with time, as I said, and the angle with which you hit this changes how far it bounces and so forth. So if I want to talk between New York City and Denver, typically I'll have to go through 2 hops to get there on some frequencies. Okay, this is the kind of elementary introduction to this. It's really pretty amazingly difficult physics, but anyway, what can we do? Well, we can build an ionosonde, which is a fancy sounding name for HF ionospheric radar. And we built one of those before the eclipse. So there are 2 types you can build that are readily usable. There is the vertical ionosonde and the oblique communication circuit ionosonde. We built this one. We want to add this one to our set of accomplishments with GNU Radio. This one is so easy. The amount of code it takes in GNU Radio to do this is utterly trivial. It's a handful of blocks in GRC and you've got the thing done. So the way it works is, at an agreed upon time, you transmit a pulse. And the pulse travels up to the ionosphere and back. And by the time it gets back, you have already guaranteed yourself that your transmitter is off, your receiver is on, and you can hear the return pulse. And so what do? You correlate for the transmitted pulse in the receiver. So that's done down in the software in GNU Radio. So literally, it's send out a pulse, correlate for the signal coming back, measure the interval in samples between the transmitted pulse and the received pulse, and that tells you, because of the speed of light, the up and down time. So 2 times the height of the ionosphere is the number of samples divided by the sample rate in seconds for the amount of time it took, and thus the height of the ionosphere. And we did this before the eclipse, and we're continuing to add to it. In order for this one to work, where T and R, the transmitter and receiver, are not co-located and they don't have a really good way to synchronize themselves, well, we have to agree upon a clock. So we have to both be able to tell the time the same way and know that we're on the same frequency. And so you need some kind of GPS or other time source that's good enough for doing this job, and you need disciplined oscillators so you're on the same frequency. And so then this one transmits at a known interval. This one begins listening at that same known interval, and when the transmission that comes up here and back is received here and correlates positively for that, we will again measure the interval between the time we know it transmitted and the time we receive it, and that gives you the length of this circuit. And so again, knowing the geometry between you, a receiver, and you, the transmitter, you're able to figure out the ionospheric height from making some assumptions. So what do? So in a period, we transmit these pulses over a wide frequency range. But not wide to what most of you are thinking about, but at HF, these are pretty long differences in wavelength. So let's look at it that way. This is 150 meters in wavelength, and this is 40 meters in wavelength. So these are big differences in wavelength. So you send a burp, you get a return, and you see that the E layer, which you can go over that later, we can, is 100 kilometers high at 2 megahertz. And come over here to 6 megahertz, and the F2 layer is 300 kilometers high at 6 megahertz at the same time. And so you're doing these measurements from here by listening all across here, making these transmissions and seeing these height returns. And thus the map is at each of these frequencies, you send a pulse, you measure the height, and you graph it. Okay, this is the super dual auroral radar network called SuperDARN. It's operated by Virginia Tech. And I put a picture up of this one because this one's kind of sexy. It's down at McMurdo Sound in Antarctica. And these are the transmit antennas and these are the receive antennas. So again, they make pulsed transmissions, send it out nearly horizontally, and they're trying to go over the horizon where you can still see the ionosphere over horizon on the Earth, but you still see the ionosphere, and the signal is scattered back to you at certain frequencies. And so you can measure multiple things. The distance from you to the ionosphere that's scattering, and because the frequency between you and it will shift, you will get a measurement of the Doppler that's induced by the shifting frequency from the moving ionospheric cloud. And so these SuperDARN radars, again, this picture was taken by Nathaniel, who went and put this up at McMurdo Sound in Antarctica. Okay, so this is how it works. You send out these staggered pulses at different kind of rates, different spacings, and this is in order for you to be able to tell the difference between one set of pulses and another. It removes the ambiguities when transmitting these pulses and them returning to you. And here's how it works. It transmits between 8 and 20 megahertz. It has 16 linear phased array for receive, 4 antenna interferometry array, 2 to 800 watts, multi-pulse sequences, measures these things: Doppler, spectral width, and signal-to-noise ratio. Again, the equipment doing this is expensive. And I'd like to try to use GNU radio and less expensive equipment to replace it. And so what does this have to do with the ionosonde? I'm trying to use the same piece of equipment. Like you using a USERP with different RF boards for many different things, I'm trying to use a piece of equipment in GNU radio that can do multiple things. This photo, again, is by Nathaniel Purcell, who took it in 2014. Okay, so the SuperDARN network in the northern hemisphere sits along this ring of latitudes, points north, and sends these pulses out, and it looks for auroral region returns from the ionosphere. And it maps, again, velocities, Doppler spread, and so forth. And this is the southern hemisphere. It's sparser because there's not much land except for Antarctica in the southern hemisphere. Okay? All right, our ionosonde and SuperDARN. Okay, so this is the red Pitaya. Many of you may know of it. Many of you know that this is a very well-known amateur radio operator in Europe who is a really good FPGA programmer, wrote embedded code for the zinc, which is underneath this heat sink, for this piece of hardware, which Red Pitaya put out for all sorts of reasons, but Pavel Demin is the name of the European amateur who wrote this code that allowed it to be turned into a software-defined radio, not unlike the networked USERPs, with one exception. The only transmitter and receiver on it is the D to A and the A to D. So that means Nyquist, since we're not trying to do any oversampling or undersampling or overtone work, Nyquist is the top frequency. So this works well up to about 60 megahertz on both transmit and receive. And there are 2 inputs, 2 receive channels, and 2 transmit channels. Gigabit Ethernet to your computer. So we want to try to use this for both the ionosonde and the SuperDARN radar software-defined radio. And we'll write all the code in GNU radio using GRC and hacking on the blocks after they've been emitted. This is an overview of the hardware, which again, you can download these slides after the talk and figure out what things are. But we have a dual core ARM A9 with the FPGA on it from the Zinc. 512 megabytes of DDR3, so you can put code on it, buffer it when need be, send stuff out the gigabit Ethernet port over to your code running on some other computer. The Ionosonde will use a Raspberry Pi. For both the near vertical and the oblique, we'll use a Raspberry Pi with an external GPS disciplined oscillator, driving both this piece of hardware and the getting timing, et cetera, in the Raspberry Pi. So this is super cheap. So let's suppose we want to use this to replace the SuperDARN transmit and receive equipment, not including the amplifier, which this will only put out a few milliwatts, and the amplifiers, as you saw, were hundreds of watts. Okay. This is $273, maybe up a little more than that now. It's $300 or less, and as you already know, the Raspberry Pi is super cheap, so you have to have a box or so, some cabling and power supplies, et cetera. So it's way under $1,000 to build our Ionosonde, hardware for that's inside the Radio Shack, and for the SuperDARN radar as well. Now, how well do these things perform? There are a few problems. Okay, so this is an ugly number, truly ugly. The isolation between the two receive ports is less than 50 dB, so that will not work. Okay, so is there something that I can easily fix? Well, they decided to have 50-ohm coax running into a single op amp, and then the op amp drive the ADCs, and internal to the op amp is a ton of leakage. So we've done our surface mount rework station, pull the op amp off, put transformers on it, and the isolation goes way up. We're still tinkering with the exact right way to do this, exact right transformer selections, and the student working on this for his master's thesis has not yet finished that work, but it should come out shortly. He wants to graduate at the end of this year, so he's got an incentive. Okay, so the minimum discernible signal in 500 hertz is minus 120 dBm, measured by me at 5, 10, 15, and 20 on a single port with 50 ohm dummy load in the other port to help get rid of the isolation problem. Alterations will improve these, but not yet finished, as I said, because the student's working on his thesis. A student's named Paul Kennedy. He wants to be an ionospheric scientist, and he wants to help replace all of the antiquated equipment. Literally, the parts are not made anymore for this equipment that goes into the SuperDARN radar all over the world. So they've got to do something, and we're trying to do it with GNU radio in this part. Okay, so this is Nathaniel right there in the white shorts. And he has a citizen science experiment. This is HF and passive. Again, it wants to use simple hardware. We're going to try to use the red Pitaya for several reasons, which I will go over. This is not a great graph of the world. Each of these arcs is on one end a transmitter and on the other end a receiver. And here's NOAA telling you that right at that time, there was a massive sun event. And so a bunch of things changed at this place right here, and the only way you can see that is the graph changed quickly. So the difference between this and this, where you see high density of these arcs versus low density of these arcs, is the low density, high density was along this line, and the low density arc is along this line. So you had a geomagnetic disturbance, and all of a sudden these paths disappeared. And so how do we get these paths? Well, amateur radio operators and others transmit a lot of stuff that allows you to measure paths all over the place. And they even voluntarily give up their equipment to make these propagation measurements. So some people are just having communications with each other, and some people are on purpose transmitting signals for the purpose of sounding the ionosphere. So PSK Reports looks at people who are having conversations using a mode of operation known to amateur radio operators as PSK 31. And all of these people, when they talk to each other, if they enter their logs into a database, they're accessible. They're publicly accessible, and we can include these measurements in these graphs. WSPR is the weak signal propagation reporter put together by a Nobel laureate, Joe Taylor. He was the person who discovered the binary pulsars and saw Einstein's equations worked by looking at that at Arecibo. He's a brilliant man. He's done a lot of great work for weak signal work in amateur radio, including making the WSPR for propagation. So I send a burst of known signal, and every single station in the world that hears my burst reports the signal strength to a database that we all can see. So every time one of these receipts is made of my signal, it goes into the database and an arc is drawn. Okay, the reverse beacon network, all sorts of signals are on the amateur radio HF bands. And the reverse beacon network listens for all of them, demodulates them, and if there's enough identifiable metadata that the station's location and other things about that station are available, that goes into a database and an arc is drawn, and that's called reverse beacon network. The same Nobel laureate that did WSPR put together a new communications method called FT8. It's highly error-corrected, multi-level FSK, and it's sent at very weak signals, and lots of people are using it to transmit to each other on the amateur radio bands, and other stations listen for them or report that they've communicated with the other stations, and all of these communications happening here, whether you're passively listening or actively communicating, go into the database and an arc is drawn. So all of these modes are used to draw these arcs. And the quality of data that tells you about signal strengths and other is variable, because people might lie about the power they're transmitting, or you don't know what antenna they're using. So there's some variability here we need to work on. So we need metadata to help. So metadata and signal data, all these things are needed: station ID, configuration, geographic location, center frequency bandwidth, etc. All these things need to go into a database. And so the people at Haystack Observatory have done us all a favor and put an out-of-tree GNU radio block together to do all of this and an IQ with it. And it's the MIT Haystack Digital RF Data out-of-tree module. It's available at this GitHub address. And so they call it their digital RF out-of-tree module, and you can download it. I'm going to go ahead and buzz past this, but it'll be in the slide deck after the talk. Okay, this is the web page, HamSci Personal Weather Station Project. Go to hamsci.org, and it's the first link. So Nathaniel Fursell, the guy I've been talking to who is at NJIT, and the person responsible for this are together, and he's at MIT Haystack Observatory, are putting together this personal weather station, which you can click on right there. And we're going to try to do the digital ionosonde, the SuperDARN radar work, all of these other things, and try to do some propagation reporting. And why am I telling you about it? Because if you want to, you can help. You can be non-amateur shortwave listener with some kind of equipment and help us passively observe these signals, or you can actively participate if you are a licensed amateur radio operator, and you can transmit on any frequency for which you have the FCC or your own telecommunications authority's permission to transmit. Amateur radio operators have several bands. And that's me if you want to talk to me about it. That's it.
Thank you very much, Bob. So I have a quick question about the bit there you said at the end before I open up to the audience. We have the amateur radio licensing exams tomorrow, so everyone here could get licensed if they're not already. What level do you need to be licensed at in order to transmit?
Okay, so if you want to transmit and transmit in everything I said, you need to have the general class license. So the introductory license is the technician class license. It gives you VHF, 50 megahertz and above, and some frequencies below 30 megahertz, but not all. All of the frequencies and modes that I talked about today, if you're going to participate in all of them, require the second level of license, which is the general class license. And let me tell you about amateur radio licensing. It's gotten much easier than it was. You're no longer required to do Morse code at all. And the questions and answers are published by the Federal Communications Commission that will be on the exam. So if you have a modicum of electronic knowledge, you can easily pass these tests. And after that, it's memorization. The memorization required are understanding the rules and regulations of the FCC Part 97. Those are the rules that govern amateur radio operation.
I also want to point out that you can, tomorrow, if you're currently unlicensed, you can test through all 3 levels, or as far as you want. You can take the first test, you can take the first test and the second test, or you can take the first and the second and the third. So you could test all the way through the top level of licensing in one sitting, assuming you pass each one along the way. Okay, so with that, do we have any questions from the audience? Right here, Yuha.
Hey,
Thank you for the
Yuha,
cool
we haven't
talk.
met before. Nice to meet you.
Yeah. Thanks for advertising digital RF. We put a lot of work into it. It includes an HF radar,
Yeah.
spread spectrum radar implementation that I wrote.
Yeah, your multi-antenna radar, that's fabulous. I'm glad you're here.
One other comment. Catherine McWilliams and her group are working on a USRP-based receiver
I knew that.
for SuperDARN as well.
I knew that. And so some of that's being deployed in Canada and Europe and other places, but the one in Canada has gone online. I'm really trying to make it accessible to people that don't want to spend that much money on the hardware.
So are you going to open source the code that you're
Exactly.
developing?
It'll work on, look, the nice thing about GNU Radio source code is if it's open, like Yuha is saying, you can put it on any of the hardware that the GNU Radio companion and a sync and source will work in.
Have you solved the problem of synchronizing these things?
Yeah, so let me tell you how we did it for the vertical ionosonde. We listened on the receiver for the transmitter and cross-correlated. So we knew when it started, we knew when we received it. That one was easy. The oblique one will not be easy. We will have to have a disciplined oscillator and time-marked data in order to do the work because we won't be able to necessarily hear the direct path.
And why didn't you use continuous, 100% duty cycle for the HF radar?
I'm sorry, I missed that.
You didn't use 100% duty cycle. You sent pulses, right?
Yes, pulses.
Okay.
They were chirp and other things. We tried all sorts of things. In the end, the chirp worked the best.
Okay.
And so we were cross-correlated for the chirp, and of course that compressed it to a single line, and it just worked great.
All right. Thanks.
And thank you for all the work you guys have been doing. I'm very happy to see you here.
Any other questions? Oh, right here.
Is WWVB stable enough to use that as a time reference to get the, sync the 2 receivers? Or?
So it's okay, but probably not good enough for what we want. And there's a problem. The U.S. government, in its infinite wisdom, has said it's going to close them.
Are they shutting down just the HF, or are they shutting down the 60 kilohertz too?
All I know about right now is they're talking about shutting down 5, 10, 15 megahertz, the HF things. I don't know about the 60 hertz stuff. I just don't know. 60 kilohertz stuff. I just don't know.
Any other questions? Oh, over here in the back. Do we have any on the other side? No? Okay.
I was just wondering if you had considered looking at the Northern California DX Foundation has a global network of beacons already up.
That's the RBN stuff. Oh,
Right.
I'm sorry, NCDX. Yes, I'm
Yes.
sorry. He is correct. There are Morse code beacons all over the world. And so they are more than useful to, with rough estimations of time, deciding whether or not that signal is present. And so that, again, will be an indicator that there is some form of propagation between those known locations at known times and your passive receiver. And there is automated software-defined radio code which will control your radio for the receipt of those Morse code beacons. Thank you for reminding me. I should have put it up there. So the one issue is it's not quite enough data density, but it's more data. More data is good data.
All right, we're just out of time, but it's okay. I can't say no, Doug.
What did you have in mind for amplifiers and antennas?
Okay, so for the ionosonde, the ideal antenna that we want to use is the Wallops Island zigzag LPDA. And that is the craziest looking antenna you've ever seen. So I will be putting it up on the hamsci.org, but you can find it, and it covers 2 to 10 megahertz well. But it's an insane looking antenna. It requires 4 35-foot masts and 1 kilometer of wire. Okay, so the ones we used for the Eclipse, we used single frequencies in various bands, and those were multi-band dipoles on transmit and receive. So we picked a frequency on several different places and transmitted on each of them in a single frequency tuned dipole, and we had multiple of them. And then we had a set for transmit and a set for receive. So we didn't have to worry about switching.
All right, let's thank our speaker. Thank you very much, Bob.